The mic's working, everyone can hear me? It sounds like it is. Yeah. Good afternoon now. Thanks for the introduction. My name is Josh Watzman. I work on the HHVM and Hack teams. Hack is Facebook's dialect of PHP, notably including a strong static type system, and that's what I'm here to talk about today. The heresy of combining type systems with PHP, the sort of things we had to do in order to make such a combination hang together, and the things we had to do in the implementation in order to do that at Facebook scale. So I'm going to be dividing this talk into three major parts. The first part is going to be an introduction into Hack and PHP, for those of you that aren't familiar with either or both of the languages. Then I'm going to go through a bunch of examples of idiomatic PHP code and talk through some of the things we had to do in order to correctly type code that people were already writing in PHP when we wanted to convert it over to Hack. And then finally, I'm going to go into some details of the actual implementation of the type checker, which is this separate OCaml system that we have that actually enforces the type system in the Hack language. So some background on Hack. As I said earlier, it's a dialect of PHP developed at Facebook. It is strongly statically typed, but it is also gradually typed. That means that there are places where you're expected to write type annotations such that the type checker can enforce them statically. But if those annotations are missing, that's also legal. And the type checker will just assume that you know what you're doing at those places and let anything pass through. This gives it full interoperability and backwards compatibility with PHP. Most of the language looks a lot like PHP, and so the Hack type checker just views PHP code as completely untyped Hack code. And this makes it hang together fairly well, enough that over the course of 2013, we actually converted Facebook's tens of millions of lines of code in its front end over from PHP into Hack, and Hack has been running Facebook.com since the end of 2013. It's been in production for a long time now. It is unfortunately a terrible and ungoogleable name for a programming language. I won't go into the history of how we landed there. It seemed like a good idea at the time. The language has lots of other cool things in it, notably including collections and async functions, and on and on and on. I'm not going to be touching on those things today. This is focusing on the type system. You can go to hacklang.org in order to see the details of the language. The runtime is the HHVM project, which is Facebook's just-in-time compiler for PHP and for Hack. That's available on GitHub here, and the type checker for Hack is part of this project. So this is all open source if you want to check it out. So a little bit of background on PHP. For those of you that aren't familiar, it is a very dynamic scripting language for web development. It has an extraordinarily loose type system, and I can barely even say type system with a straight face when talking about PHP. It's all enforced dynamically in a couple of strange ways. It has a bunch of holes in it. I'm not going to go into the details of all of that. Basically, PHP is a dynamic scripting language. We're adding static types onto it, and I'll call out specific gotchas in PHP as they become relevant in some of my examples. So here on the left, this is what some PHP code looks like. The syntax should be familiar with anybody that's done any sort of C or algol-derived language. It's all kind of the same. PHP files notably start with question mark, less than question mark PHP to indicate it's a PHP file. And then I have two functions defined here. An increment function that does what you'd expect, takes a value and adds 1 to it. And this function f, which calls increment with the value 42, prints that out. And so if I were to invoke f here, I would print 43 to the console, as you'd expect. Here's what the corresponding Hack converted code would look like on the right. It basically looks the same. Again, Hack is a dialect of PHP, and the idea was to be able to convert cleanly from PHP into Hack. The major changes are that we've changed the opening tag to HH to tell the Hack type checker this is Hack code. We've added integer type annotations on the increment function. It's explicitly annotated now to take and return an integer. That's probably what you intended anyways when you wrote this on the left, and we've just made that explicit. And then the function f, it doesn't return a value, so in the C parlance, it returns void, and all the rest is the same. So a couple things to note about this that aren't immediately obvious. The first is that this local y in the function f, there's no type annotation there. There's no variable declaration for that matter. We do local inference in order to know what the type of all of your locals are, including generics when we get there. The annotations are only required and in fact only legal at function boundaries. Function parameters, function return types, and class members, object members. The second thing is that the 3 places that I have written annotations here, they're all optional. This would still be legal hack code on the right if I omitted any or all of those. And in fact, the only reason that I've written them in here on the slide in the first place is for illustration purposes, and so that the code on the left and the right doesn't look identical. But it's legal to leave any of them out, and the type checker will just assume you know what you're doing. So PHP. Unfortunately, the image doesn't show up too well on the slide here. This is the famous, iconic double-clawed hammer of PHP, built by a guy named Ian Baker off of a rant someone else wrote called PHP, a fractal of bad design. PHP gets a lot of flack. It deserves most of the flack, but there are also a lot of really good things about the language that I think and Facebook thinks has served us really well. The first one is its request isolation model. When you start a request or a script execution in PHP, you have nothing except the code that's executing. There's no global variables, no global state. Any of that must be explicitly loaded from the file system or from the database. And at the end of the request, everything is thrown away. And anything that you save must be explicitly persisted to the file system or to the database, to memcache, whatever. This means you've got no pollution of global state. It's a really nice mental model in order to work in when doing web development. The other very nice thing that it has, and the thing that was most important for us to preserve in Hack, was its really fast iteration cycle. PHP doesn't have a compilation cycle. It doesn't have a type checking cycle. When you edit code, you save it in your editor, you go over to your browser and refresh, and the changes are visible immediately. There's no latency there. And so when we were adding a type system onto this, it was very important to us to design the type system and design the type checker such that we maintained this really fast feedback loop. And that's sort of at the core of a lot of the way we've designed a lot of these things. But PHP is PHP. It's a sort of thing that inspires people to build literal double-clawed hammers. And so type systems in PHP are kind of a heresy, leading to the title of my talk. The hardcore PHP folks sort of view a strong static principled type system as, what the heck are you doing? You've got types in my PHP. And on the other hand, you've got the academics who might be saying, what the heck are you doing? You've got PHP in my nice pretty types. Which are both true. And so the system is really fun to work with, but it seems to hang together pretty well. And at least at Facebook, and from what I've talked to from folks outside of Facebook, people seem to like it. But it does mean that there's sort of one key overriding theme to this talk and to the language, which is important enough that I've made an obnoxious word art animation out of it. Pragmatism. Hack is what you get when you try and shoehorn a type system onto PHP. It's really good ideas from the literature and from academia of how to do type systems and how to hang these things together, but applied in sometimes unpleasant or unconventional ways in order to make it work on a really dynamic language and a less principled language like PHP. But it works. It runs Facebook's tens of millions of lines of code, and folks outside of Facebook, other companies, are beginning to adopt it now. People seem to like it. So now, for the second part of the talk, an overview of the hack type system and some examples of idiomatic code. So some things to keep in mind. Let me go down this list. The most important one, and it's kind of a weird one, is that everything is only one step away. What this means is that we aren't doing global type inference on hack code. That's what I said earlier. We require annotations at function boundaries. Require in the sense that if it's missing, we just assume we know what you're doing and don't try to infer it. It's allowed to be missing, but we won't try and infer it. That means that if function f calls function g, in order to type check function f, we only need to look at the signature of function g and not its body. This gives a few interesting complications later, but has a bunch of nice properties that sort of make this whole thing work. But it is also fairly pervasive through the way the type system works, so it's important to keep in mind. The next two things are the pragmatism that overlies the language in typing code that already exists. We wanted to convert Facebook's PHP frontend into Hack, and so we're converting code that already exists, and so we had to type code that already exists and design type system features for that. So this means we have lots of features to just let you write idiomatic code, and some interesting edge cases that we inherit from PHP and the way people write PHP code. Finally, for those of you that aren't familiar with deep type systems, don't worry. There's going to be no inference rules and no proofs in this talk. This is the only Greek letter that appears here, and it's just as a joke. We care, like Facebook and the Hack team do care that there is really solid theory underlying the things that we're doing, but we're trying to build a practical system that we're deploying to Facebook, and so we don't want to spend the months or years that it would take in order to sit down and formally prove the system correct. That's not really what we're after here, so that's not what I'm talking about. We care about correctness and care about fixing bugs as they become apparent, just not the huge formalisms. That's not the space we're in. Nothing wrong with that, just not what we're doing here. So again, this part of the talk, looking into type system features by way of examples of idiomatic code. So the first one is how we deal with scoping. PHP doesn't have variable declarations, and it's really nice if you want to know what things exist. So here's an example of some PHP code, or sorry, this is some hack code, but it's idiomatic PHP. You just poof the variable x into existence by writing to it, and so we would like to know that x exists when you return it. And this example is really simple. Whenever you use the x as an L value, you write to it, and so we know x now exists, and we can track that, and it's of type integer. Variables are just introduced by writing to them. This is really simple. It gets slightly more complicated whenever you have code like this. Notice x is not defined or written to before the if block, and so we'd like to see that since x is defined in both branches of the if, we would like to be able to use x when you fall out of the if. So we can say x is defined here in the true branch. It's also defined here in the false branch. We do what was on the last slide in order to figure this out. And then whenever you come out of an if-else conditional, you can see intersect all the variables that are defined in both. And so we know x exists when you pop out. Again, nothing complicated here, but it gets one step more complicated whenever you have code like this. Something that interrupts the normal flow of execution. You have we call this a terminal branch. This else here. It throws an exception. If you land in the else, you can never get down to this return. And so we need to know x is defined here. We need to have a notion of terminality so that people can write code like this. It turns out this is a fairly common pattern that we see at Facebook. So we need to understand this, that this is terminal, and so we don't do the intersection there. Just what's defined in the true branch is defined after the conditional. Nothing terribly complicated, but it gets a little more interesting when you start doing these conditionals where the type isn't the same on both branches. And you need to start figuring out, the crux of the issue is, what is the type of the variable when you pop out of that conditional? How do you deal with type inference with implicit subtyping, which is what we have here? For those of you that are familiar with the literature on type systems, solving this in the general case with global inference is actually undecidable. So how do we make it decidable? What do we do? Again, here's an example of the crux of the issue. I have a conditional. I define x, and it's going to have type A. I define x here, and it's going to have type B. So what's the type of x when you pop out of here? And in particular, when I return x, is that legal to use x as a thing? And so to sort of get an idea of why this gets undecidable pretty quickly, what is the right type for x? Are A and B subclass and superclass in one direction or the other? Is thing a superclass of both? Where does thing fit in? Do A and B implement some common interface? Maybe thing is that interface or some super interface of it. Maybe they implement like 15 interfaces in common. So what do I pick for the type of x? And so the answer is we don't. We say that x is unresolved of A and B. We delay the decision. X is sort of the superposition of both A and B. And so when we hit this return x, that's when we, to continue the analogy, collapse the wave function, when we resolve the unresolved. We can see that either A and B both work for returning a thing, or one or both of them doesn't. So we can delay that decision until we hit the type annotation of thing. And the existence of the thing type annotation is what makes this tractable and, in fact, decidable. If that annotation is missing, we just throw our hands up and go, you're missing an annotation, you must know what you're doing. Again, everything is one step away. We're not doing global inference, so we don't have to solve the problem in the general case. We can just delay it like this. Again, for those of you that are familiar with type systems and programming languages, this unresolved might look sort of like a union type. And on this slide, it's behaving largely like one. But it turns out that unresolved doesn't quite behave like a union type. And let's look at some examples of that. So first, let me talk through this code for those of you that aren't familiar with PHP. This is a function f. It returns a vector of mixed. Vector is a hack collection like the C++ vector, and generics in hack work much like they do in most languages. So this vector is allowed to contain elements of type mixed. Mixed is the name for the supertype of everything in hack. So anything is a mixed. This is a vector of anything. Here I create a new vector with this syntax on the first line. And then this v bracket bracket is a list append in PHP and in Hack. And so I'm appending the value 1 and then the string high text to it, or sorry, high test. So you can see, sort of looking at this code, this should be legal. This vector I'm saying is allowed to contain anything, and ints and strings are both anything. So how do we deal with this? What's the type of the vector when we first create it? How are we inferring this generic? And so we say this is a vector of unresolved of empty list. It's some superposition of something that we haven't decided yet. And so when I stick the integer in, I say, well, it's unresolved of int. And then when I stick the string in, now it's unresolved of int string. And then when I return it, I can see that, OK, vector matches vector. And then I can check the unresolved against the mixed. And to check the unresolved, you say int and string both work for mixed. Everything works for mixed. And so you're good. So this looks a little less like a union type. This unresolved is allowed to grow and grow and grow. But here's one more, even more interesting example of how this really doesn't look like an unresolved anymore. This is the same example as on the last slide, except instead of returning the vector, I'm passing it into another function, this function m. In technical terms, I'm using it in a contravariant instead of a covariant position, which is extremely important because I can do the same sort of inference here. But I've got to be very careful when I pass it into the function m. This vector of unresolved int string says this only contains int and strings. But the vector of mixed, this function m, takes it as a vector of mixed. And so it could put things into it that aren't ints and strings. It could put some Boolean into it, or whatever you want. And so whenever we use this, whenever it hits a type annotation, whether in a covariant or contravariant position, although it only really matters in this example here in the function parameter position, whenever we hit that, we have to actually resolve and collapse the unresolved. So the type of the vector actually changes as a result of this function call. We resolve the unresolved, we collapse the wave function to whatever the annotation was in this parameter. It's now actually vector of mixed. The unresolved goes away. We don't know what happens to it anymore, other than what that type said. As an aside, for those of you that are familiar with the way Hindley-Milner type inference works, I'm eliding all of the type variables here. This is actually like vector of alpha, where alpha is unresolved of empty list, and so on and so forth. Like the system does work as you'd expect for Hindley-Milner type inference. It just isn't terribly important for the purposes of this talk, so I'm eliding all of the type variables. So flow sensitivity. We just need to understand idiomatic language constructs. One of the obvious ones and the most important ones is nullability. Thankfully, when PHP had its bare bones type system, everything was not nullable by default. They had a very bizarre way of making things nullable. We made it very nice by just saying int is not nullable, but question mark int is nullable. The question mark makes something nullable. And so this function takes a nullable integer and wants to return a non-nullable integer. It wants to do it, as you'd expect here, by checking for null. If it is not null, use that value, and if it is, return some default. And so the type checker needs to understand this. In particular, it needs to know that x is no longer a nullable int, it's just an int. Whenever you hit the true branch of this if, it needs to understand null checks like this. Not particularly complicated, just we had to go through a bunch of the idiomatic code that people write to understand core constructs like this. Another one being instance of. I won't belabor this example, but we do a similar thing with instance of to know that this x is of type I, but when you check instance of C, when you land in this true branch, it's now a C. And you're allowed to call things that are on C and not on I. Excuse me. So this gets one step more interesting and more complicated whenever you hit member variables. So here's a similar example to my one 2 slides ago with nullable int. Instead of being a parameter, it's now a member variable. It's potentially nullable, and we want to return a default value if it is null and just use the value if it isn't. And so you'd expect this to work. This is how you'd write it in an idiomatic PHP. And this, as a matter of fact, it works in Hack. But we've got to be a little bit careful here. This arrow x, it isn't a local. And so we need to basically promote it into local scope as far as the type checker's internals are concerned, such that we can change its type. And so this is what we call fake locals. So we promote this arrow x as if it were kind of a local, so that we know that its type has changed from nullable to not nullable, and then allow people to use it. But fake locals are not quite like normal locals because they're not local. So this is a type error in Hack. And the only thing I've done is added a call to the function foo here in the middle. Why is this an error? Why is this bad? This is why. We could have another function over here called gotcha that resets this arrow x back to null. And again, since our type inference is purely local, we don't know what the heck foo is going to do. It might have another reference to the current object and call gotcha on it and reset it back to null between the time you do the test and do the usage. So anytime you make a function call, we have to throw away all of the fake locals such that we can get cases like this correct. It's a pretty pessimistic approach to it. It's kind of painful and we get a lot of questions about it, but it's what we have to do in order to ensure correctness while still being able to type this idiom at all. So another thing we had to deal with in this type system, since variables aren't declared, since variables can change types, is how do you deal with non-local control flow, with exceptions in particular. So let's look at this example. I have this function that wants to return an integer. I originally have this x, which is a float. Then I articulate splines. Then I say that x is 42. Now it's an integer. Then I frog blast the vent core. Now x is still an integer. I return it. That's legal. And 0 is clearly also an integer, and so this code works. However, this is in a try-catch block. And so reticulating splines or frog blasting the vent core, either of those could throw an exception and land me here, and I have no idea when that can happen. And so if I do this, if I return x instead of the constant 0, I need to know what the type of x is. I could have landed there from here to here, like I said a minute ago. So what do? What is the type of x here? This should be an error, and so how do we track that? And what we do is actually for every local, we're tracking two types. I've been showing you just one of them, which is what we call the current type. But it's actually a pair, the current type and the list of all types this has ever been in the current scope. And so what this looks like is when you say x equals 3.14, we say x is a float, but the list of all types is unresolved of float. It's another sort of superposition type, an unresolved type. Then when you make it an int, we say it's unresolved of float and int. And so when I go down here and return x, the current type of x is int. And so this is legal here. But when you land in a catch block, since we don't know where you came from, we have to use the list of all types and promote that into the list of current types, or into the current type. For reasons that are lost to history, we call that integration. That's the function in the type checker if you go read the source code. And so x now, its current type becomes unresolved of float int, and float is not compatible with int, and so this code gives an error as it should. One of my favorite bizarre things that we do that has to do with a similar problem is the loop fixed point. Here's some pretty perverse code. It turns out this is not just an academic example. This is distilled down from a bug we actually had reported to us by real product code that we were mistyping it because we weren't doing this properly. The crux of the problem is that the types of these variables keep changing each iteration around the loop, right? They're initially all integers, but every time you do one iteration of this loop, they might become a string. And so we have to do a similar trick where we're tracking unresolved types and keep iterating the type checking of a loop until we hit a fixed point of what the types might be. And so we know that depending on how many times you go around this loop, which we don't know statically, it could be either an int or a string, and so we have to assume it could be either one in order to get this right. Sorry, I'm trying to thought. This is a really annoying performance problem. We've had to rewrite this code several times. You can imagine once these get nested, I think our original version of this was like exponential time, which is what a naive implementation will be. I think we have it down to like cubic or something. I don't know. It's still not fast, but it's better than it used to be. Here's another, I'll flip through this really quickly. Another example of something you'd like to work, but doesn't right now. Two interfaces, foo and bar on each interface respectively. This comes in as one interface. And so I'd like to be able to call foo regardless of what happened in the middle. But because of the way we implement the type changing here, I won't go through the whole reason for this. Making this work properly, this ends up being an unresolved type. Unfortunately, if you talk to me offline, I can go through the full example. The gist of it is we would like this to work. We need something called intersection types in order to track that it's both things. We could, in principle, add them, but they distribute over unresolved types, and so when we tried to implement it, it got way too slow. There are various clever things I think we could do in order to make this example not be so painful, and we just haven't gotten around to it yet. But it's the sort of thing, it's like, we would like this to work, but we can't. It's too slow. We need this to work at Facebook scale. And it's one of the annoying compromises we had to make.
When you say it's too slow, is that the compilation is too slow or the runtime is too slow?
The type checking is too slow. I'm happy to address questions at the end, and I can go into more detail on that if you'd like. OK, so now moving into the final part of the talk, which is on the implementation of the OCaml binary that actually enforces this type system. When we do type checking, the way we've implemented it is in 5 phases. The details of the exact what's going on here isn't super important. I just want to run through it briefly. We parse everything into an AST. Then we build something called the global environment, which is basically a set of all of the functions and classes that are defined. We need that in order to do what we call naming, which is resolving all of the names that exist, and generally dealing with scope and massaging the AST into something nicer. Then one of the most important phases are declaration and typing. Declaration goes through all of the named bodies of the functions and extracts out the signatures of the classes and the methods that are defined. So we know there's a function f that takes an integer and returns a Boolean. Then typing uses those signatures in order to actually do the type checking of the bodies of everything. I've blown through this quickly enough that it probably isn't necessarily obvious, but you think about this. This has been carefully constructed so that it's trivially parallelizable. In particular, declaration and typing is where you can see this. In order to type check the body of something, you only need the declarations of everything else. You don't care what else is being typed right now. We've extracted the information we need during declaration. Everything's only one step away. You only need the signatures. We're not doing global inference. And, well, that means we can multithread it. Computers have lots of CPUs. Code has lots of functions. Wouldn't it be nice if we could just dole it out? And it turns out we constructed the system such that you can do this. The annotations at the function boundaries are what make this tractable. The phases themselves basically are just synchronization points in the parallelism where we farm out a bunch of things, the computations are done, bring it back together, now you farm out a bunch of things using that data. Each phase only depends on data from the previous phases, which makes this actually really nice. Now, the type checker is implemented in OCaml. For people that have used OCaml, threading in OCaml gets kind of exciting. My personal opinion, the opinion of the team at the time, and I think the opinion of most OCaml programmers, OCaml has a thread abstraction, and it's completely useless. I shouldn't say completely useless. It's not at all useful for what we want to do here. I believe it is concurrent but not parallel, or it like runs into all sorts of issues with the garbage collector when you try and make it parallel. It wasn't suitable for what we're doing. I hear there's work on this. Hopefully it will be in the future, but at the time it wasn't. So if you can't use threads in order to multi-thread, what do you do? So what we ended up doing, sort of the next obvious thing, is using fork. Use multiple processes. Now you have no shared anything anymore, which is actually kind of a nice model to program in. Nothing's shared. But now you do need to share data, like these ASTs that we're building up. How do you share data? The obvious answer, and what we originally did, was using IPC. We used, I think, Unix domain sockets, something like that. You serialize a bunch of data, shove it over, and deserialize it on the other end. We did this for a while. It does work. Excuse me. But it turns out that you end up duplicating a whole lot of data. There's a lot of complication because now you have the processes aren't homogeneous. You need to have some that are holding on to the data that you communicate back and forth to. It's kind of a pain, both conceptual and implementation-wise. So if you don't do that, then what do you do? And this is sort of a weird answer. Our tech lead ended up thinking of this. There are a pair of flags you can pass to the Unix mmap system call. Map shared, map anon. What that does is say, this region of memory, give me this region of memory. And when I fork, map the same physical frames into my address space each time. Effectively, it says this region right here is shared between the forks, just like everything is shared in threads. There are various other ways of doing this. We use mmap. So that means you can map this region, you can fork all of your workers, and now they have this shared space to play around with. Their OCaml garbage collected heap is still separate because we've forked everything. It's just this one region that we can manage with some special code, some special C code linked into the binary that makes this work. So what is in this region is a shared lockless hash table that's shared among all of the processes. By the way, I'm going to start using process and thread interchangeably at this point. You understand what I mean. It is thankfully immutable data. It is these ASTs and other computations that we've done. But it's still a lockless data structure with a wad of very exciting C code managing it, which leads to things like this. You can't see segmentation fault core dumped here on my slide, but that's what it says. So like, for people that have done lockless data structures, they are very exciting and very fun to implement and have all sorts of bizarre concurrency bugs. So how do we manage this? It turns out that this is tractable for us because there are a bunch of nice invariants that we can have over this shared lockless hash table because of the way we're using this data and what we're doing. I'm going to go through some of the invariants, and it's worth keeping in mind that they're sort of obviously useful for hack and for this type checker, but they also turned out to be just as useful for Flow, which is our type system for JavaScript that we open sourced about a year ago. It's actually built on the same OCaml base, same code. These are surprisingly widely applicable. So the first one, and probably the most useful, is that one thread and one thread only will ever be touching the hash table when you're doing a delete. You don't have to worry about concurrent reads and writes with deletes. Because the deletes only happen whenever you're incrementally updating state, and you can sort of synchronize everything and say, like, I am invalidating this part of the hash table. I'll talk more about incremental mode later. This gets rid of like the nastiest class of lockless data structure problems, people that have studied them at all. It's always like concurrent inserts and reads aren't easy, but they're fairly tractable. They're not conceptually that hard. And like, you know, whenever a professor gives a lecture on this, he'll spend 5 minutes talking about this, and then he or she will spend like the next 45 or 50 minutes talking about how to do deletes. And so we got to just throw the whole problem out the window, which made us very happy. The next thing that we have, the next two invariants come down to basically whenever you're reading and writing data at the same slot in the hash table, even if two threads have computed it, it is equivalent data, and so it doesn't matter who wins the race to write it and read it. And furthermore, if someone's writing while someone else is reading, as long as they either get all the data or none of the data, it doesn't matter when they see it. Because if they don't see it, they can just go off and recompute an equivalent version of it. It becomes a performance problem, but not a correctness one. And so if you're inserting and reading, we don't really care when the read becomes visible to an insert from another thread. Now, if you've really been paying attention, you might be asking me right now, but wait, I said that the phases only need data from the previous phase. When am I ever reading and writing to the same slot in the hash table? And it turns out that what I said about the phases isn't quite true in one place. That turns out to be actually really important and make this come up. And it comes down to declaration and inheritance hierarchies. For performance reasons, whenever we want to do a declaration of a class, we need to inline the declarations of all of its recursive superclasses into it. Whenever I call the class foo function f, when I want to look up the signature of f, I don't want to have to traverse up all the entire inheritance hierarchy of f, particularly since PHP has something. It's not quite multiple inheritance, though we model it that way in the type checker called traits. You can go up pretty far without that deep of inheritance hierarchies before you might find it, and so we need to inline all of this. This means that when we're declaring, cat, we need to declare mammal first, and to declare mammal, you need to declare animal first, so you can inline these all the way down, and so you can get these problems in the type checker if one thread is told to declare cat, one thread told to declare dog. Cat might see mammal doesn't exist, that might see that animal doesn't exist, and dog is somewhere in the middle of doing all of this. Maybe the cat thread is finished doing mammal by the time dog is trying to see if mammal is there, and so you run into these contention over the same slot. But thankfully, like I said, there's equivalent data, so maybe cat will or won't have written the data for mammal by the time dog tries to see it. And so it doesn't matter, dog may have to go off and recompute it, that would be too bad, but it's a performance problem, not a correctness one. Similar things can cause concurrent inserts, but again, this one isn't too bad. It's equivalent data. One of them wins, the other gets dropped on the floor. Oh well, too bad. The one invariant that we do need, and that we didn't know for about 9 months after we implemented this, and that led to some really fun bug hunting, is this one. That within a single thread, once you write data into the hash table, that thread does need to be able to read either that data or some equivalent data back. It's not permissible for a write to not be visible to the same thread. And if you go back to thinking about how we're doing the inlining, this does make sense. If I'm trying to do cat and then I do mammal, when I come back to finish cat after having finished mammal, I expect the data for mammal to be there. But we didn't realize this for about 9 months, which led to basically a bunch of methods that were supposed to be in superclasses just not being available in subclasses. Very rarely, very randomly. The race window for this was fairly small. So it was a pain in the butt to track down. Eventually, we did squash this one. It was the last major concurrency bug that we had. My favorite part of this anecdote is that the way we solved it involved an unfortunate busy loop. There's probably a smarter way, but the busy loop worked. But we needed to explain to the compiler that we're waiting on memory here, and so there's an ASM volatile in the middle of our nice, pretty OCaml type checker that makes the whole thing hang together. So I've been alluding to this thing called incremental mode. Once we have this type checker, it's nice and parallel, but Facebook has tens of millions of lines of code. It takes about 2 minutes for us to type check all of that code. That's not too bad for the size of the code base. For people that do C++, that's like really great. Our compiler for this code doesn't even link in 2 minutes. And so like you would think 2 minutes is great, but it's a no-go for the engineers that we had at Facebook working on the front end. They're used to the fast iteration cycle that they were used to with PHP, where you can save code and immediately see its results. A 2-minute latency in there would mean that this would basically be relegated to like an offline lint job or something, which is not what we wanted. You want the immediate feedback of a type system when you're like working in Haskell or something. Like that immediate feedback is great, that you see like you did something wrong, like very immediately. And so we came up with the idea of incremental mode. The realization is that we have tens of millions of lines of code, but when you're changing something, you're probably changing about 5 of them. And so we can have a server sitting in the background that has most of its state that's using the Linux kernel's iNotify subsystem to figure out when files are changing and can just update its state from there, and that the recomputation is very small. So we have to know somehow a dependency graph. Ooh, that shows up really nicely. A dependency graph such that when file A changes, what do you recompute? The way we build this up is actually really simple. We just know that whenever you're type checking function F calls function G. You have to load the declaration for G. And so the process of loading that declaration adds an entry into our dependency table that says F depends on G. Then whenever the file containing G changes, we know everything that's in a file. We can look up all those functions, get the reverse dependencies, and go and recheck all of the reverse dependencies. And again, everything is only one step away. So if F calls G, and G changes, we need to recheck F. But we do not need to do it recursively. We don't need to recheck anything that calls F, because the signature of F hasn't changed, if F itself hasn't changed. And this makes the whole thing tractable. At this point, the hard part is really determining what changed. That's just a whole bunch of thinking very carefully about the problem. Most of it actually isn't that hard. The hard part has to do with, again, the way we inline subclasses in declaration. There's a couple of gotchas there. But for the most part, this is surprisingly straightforward. So that's all I have prepared. The conclusion is basically pragmatism, 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 type systems, PHP, an interesting intersection here, some weird features in our language, and a fun implementation. I'm happy to take questions now. I believe we have a few minutes.
You have 5 minutes, but please repeat the question.
OK. You had asked about, yeah.
Well, you answered the question I asked, but I have another one.
Sure.
What about polymorphism? So the classic example of duck type polymorphism is like the identity function, identity of x equals x. So how do you type that?
So the question's about polymorphism, in particular typing the identity function, ID of x equals x. As an example, yes. So we're not doing any sort of polymorphic, sorry, that's not quite true. We mostly don't do any sort of polymorphic inference, right? If you write the identity function, then you have to write its signature in order for us to know how to type it. If you don't add type annotations, then we just throw our hands up and go, I assume you know what you're doing and anything's going to work. You can write a type signature for the identity function using generics. It's just ID of t, where x is a t and you return a t. And so we're able to properly use the generic once you've written it down, but we're not trying to infer it at function boundaries like that.
Oh, so there is a syntax for writing it?
There is a syntax for writing generics, and defining your own generic classes, yes. That they are available in the language and fairly powerful.
Did you encounter that in a lot of actual code?
The question is, did we encounter generics in a lot of actual code? Yes and no. There's a lot of generic usage at Facebook, but it's unclear how much of it actually should be generics as opposed to some other language feature. So yes, there are a lot of things that should be generic. Lots of helper functions like that come up a lot. A really good example of something that is generic, but it's not clear if it needs to be. We have a generic object superclass that knows how to load things from a database. And for bizarre historical reasons that I will not go into, the type of the identifier that you use in order to load an object can be one of several different types. You might think it's supposed to be an integer primary key. That's what it usually is, but it can be other things. And so the obvious way of doing this is that the superclass is parameterized. It's generic, parameterized over the type of the key. But the thing is, the way the type of the key is defined uniquely by the type of the object that you're loading. So for example, status updates are always loaded by an integer ID. And photos, historically, just as an example, were always loaded by a string key. And so it's not really generic in the normal sense. And so we have a lot of these that are like this, where generics are supposed to be parameterized such that the caller sort of determines this is a vector of int or a vector of string based on how you use it. But that's not the case here. The subclass uniquely determines which one it is. So we have a lot of generics that are like this. It gets very unwieldy very quickly because anything that uses that class has to be parameterized more and more and more, again, if it wants to be generic. And so the feature that we've added, it's been in the language for a little while. We haven't really talked about it much just because we haven't written up the docs for it. It's something we call type constants, which is stolen from a feature in Scala, which might be called type constants as well. I see you nodding. I don't remember the name of it. One of our other engineers designed and fleshed out this whole thing. The gist of it being that it's sort of like a generic in that it's a type parameter in the superclass, but it's not a generic. The subclass fills in the whole of that type parameter. And so a lot of code that's currently generic is being moved over to these type constants to reduce the unwieldiness, because that's really what they wanted anyways, as opposed to generics. It's a very long-winded answer to your question. The simple answer is yes and no. I think I've still got a couple of minutes if anyone has any questions.
We have slightly less than 1 minute, so
Okay.
short.
So, short question.
You briefly mentioned Flow as well.
Yes.
Like similar concept for JavaScript, right?
Yes, at a very high level, Flow is a similar concept for JavaScript. They are trying to do more in the total inference space than we are.
So they're not only strictly local?
I believe Flow is not only strictly local, no. Don't quote me on that. I have helped some of the implementation bits. What was that?
It's not.
It's not, yes. They are not doing, they're actually not even doing Hindley-Milner inference. They're doing something a little bit different.
Okay.
I am not qualified to speak on it. Avik is the guy you can Google. He's done talks about how Flow does this.
Sure, interesting. You just mentioned that they used that some of the code base was shared between the two projects, or?
Yes, there is shared code between the two projects. It's mostly the infrastructure stuff that I was talking about in the last part of the talk, how we share data in the phases and do parallelization. It is actually the same code underlying that. Okay, I'll be around for the rest of the conference. If anybody has any other questions or wants to chat, I'm happy to do so. Please grab me. Thanks.